future of everything. We've got 3i Atlas updates and maybe even our best shot yet to clearly see the third interstellar object ever detected passing through our solar system.
3i Atlas is no ordinary comet.
Do you hear about that fucking object that's hurtling towards Earth at like 130,000 miles an hour?
No, that might solve all our problems.
It's growing bigger, brighter, changing color, and shedding a gas cloud wider than Jupiter itself. Even stranger, its orbit shows none of the wobble real comets have, as if it's made of something far denser, maybe even alien.
The principal investigator of that camera said that he cannot communicate the information to the public because of the government shutdown.
I don't buy the shutdown excuse. That to me is really suspicious 8 days later that NASA hasn't released these photos. It's not like nobody is at NASA right now is able to do this.
And now, racing toward Mars at 60 kilometers per second, it's about to vanish behind the sun, leaving only a handful of orbiters to witness its most dangerous and mysterious phase.
That, of course, raises some concerns that maybe they know something and do not want to let us know about it.
Discovery and early observations. On the night of July 1st, 2025, robotic telescopes scanning the southern hemisphere sky picked up something that would change everything. These telescopes belong to a system called ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, and their primary job is watching for dangerous space rocks that might threaten Earth. The facility in Rio Hurtado, Chile, detected an unusual streak of light moving through the constellation of Libra. Within hours, scientists at the Minor Planet Center started crunching the numbers, and what they found sent shockwaves through the astronomical community. This object was moving too fast. Way too fast. Its path through space followed what astronomers call a hyperbolic trajectory, which is a technical way of saying it was not trapped by the sun's gravity like everything else in our solar system. The math was undeniable. It came from somewhere else entirely, another star system light years away, and it was just passing through. NASA gave it an official designation, 3i Atlas. That 3i prefix carries enormous weight because it marks this as only the third interstellar visitor humanity has ever identified and tracked. The first one, Oumuamua, showed up in October 2017 and caused an absolute sensation because of its bizarre elongated shape and complete lack of any visible tail or cloud of gas. It looked more like a tumbling piece of cosmic debris than anything else, and it left scientists with far more questions than answers. Some researchers even speculated it might be artificial, though most dismissed that idea. The second visitor, 2i Borisov, arrived in August 2019 and looked exactly like what scientists expected an interstellar comet to look like. It had a classic blue-tinted tail, behaved predictably, and matched models built from studying solar system comets. 3i Atlas, however, would prove to be something entirely different from both of its predecessors, a hybrid object that refuses to fit neatly into any category. Early tracking showed it was coming inbound toward the sun, positioned somewhere between Jupiter and Mars when astronomers first spotted it at roughly 5 astronomical units out. The speed was remarkable, traveling at approximately 210,000 kilometers per hour, and that number would only climb higher as gravity pulled it deeper into the solar system. Tracking the brightness. When 3i Atlas first appeared on telescope images in early July 2025, it was incredibly faint at magnitude 17. Magnitude works backwards from what most people expect. Smaller numbers mean brighter objects, and bigger numbers mean dimmer ones. The faintest stars you can see with just your eyes on a perfectly dark night away from all city lights are around magnitude 6. At magnitude 17, this comet was literally thousands of times too faint for anyone to see without a massive professional telescope. Astronomers built computer models predicting how bright 3i Atlas should become as it moved closer to the sun. Those models were based on decades of comet observations, both from our solar system and from 2i Borisov. The predictions suggested a slow, steady increase in brightness following a predictable curve. But 3i Atlas had other plans entirely. By early September, the comet had jumped to somewhere between magnitude 12 and 14, depending on who was measuring it and what technique they were using. This means the comet became about 40 times brighter in just a couple of months. That is dramatically, inexplicably faster than models predicted. Amateur astronomers with backyard telescopes started spotting it and uploading their observations to the Comet Observers database, a crowdsourced website where anyone can share what they are seeing, Professional scientists rely heavily on this network because amateurs often catch rapid changes that scheduled observatory time might miss. As of late September, different observers were reporting the comet at about magnitude 15.35, though that number changed almost daily as the comet continued its unpredictable surge upward in brightness. Here is where things become truly wild. That cloud of gas and dust around the nucleus, what astronomers call the coma, was growing explosively fast. The James Webb Space Telescope, humanity's most powerful eye in space, currently stationed far beyond Earth's orbit, measured the carbon dioxide plume streaming away from the nucleus. What it found was staggering. The coma now stretched 350,000 kilometers across. To put that in perspective, Jupiter itself is about 140,000 kilometers wide. This comet's gas cloud is more than twice as wide as the largest planet in our entire solar system. The bigger the cloud grows, the more surface area it has to reflect sunlight back toward Earth, which makes the comet appear even brighter when we look at it through our telescopes. It creates a feedback loop where more activity leads to more brightness, which leads to more observations revealing more activity. But even with all that explosive growth, 3I Atlas remains completely invisible to your naked eye. Current forecasts suggest it might reach magnitude 10 right around perihelion in late October, though comets are famously unpredictable, and those forecasts could easily be completely wrong. If it does hit magnitude 10, it would become the brightest interstellar object ever observed by humanity, though still far too faint to see without optical aid. The carbon dioxide mystery. Perhaps the most shocking discovery about 3I Atlas came when the James Webb Space Telescope turned its full suite of instruments toward the comet for an extended observation run. JWST carries an instrument called NIRSpec, which breaks down light into its component wavelengths, so scientists can read those spectra like a detailed chemical fingerprint, identifying exactly what elements and molecules are present in the comet's coma and in what quantities. What they found was unlike anything seen before in any comet, whether from our solar system or from interstellar space. The coma surrounding 3I Atlas is dominated by carbon dioxide to an extreme degree. The measurements showed a carbon dioxide to water vapor ratio of 8:1. That means for every single molecule of water vapor being released, there are 8 molecules of carbon dioxide streaming off the nucleus. To understand why this is so profoundly strange, you need to know what normal comets look like chemically. Most comets we have studied in detail, including 2I Borisov, which was the previous interstellar visitor, release far more water than carbon dioxide. 3I Atlas flips that entire script completely upside down. This ratio of 8:1 is among the highest ever measured in any comet, and it represents what scientists call a 6.1 sigma deviation from the average measured across all known comets. In plain English, that means this comet is so wildly different from the statistical norm that the odds of it being random chance are vanishingly, astronomically small. Something fundamental about where and how 3I Atlas formed must be completely different from most comets humanity has ever encountered. The spectrum also revealed traces of water ice, carbon monoxide, and carbonyl sulfide, along with various dust particles reflecting light. But carbon dioxide is the overwhelmingly dominant player, the main character in this chemical story. What makes this discovery so fascinating is what it potentially tells us about the comet's birthplace, billions of years ago. In our solar system, comets that form farther from the sun in the coldest regions beyond Neptune tend to have different ice compositions than those born closer in, where temperatures are higher and different molecules can condense. The overwhelming carbon dioxide dominance suggests 3I Atlas might have originated in an extremely cold region of its home star system, perhaps in a zone where carbon dioxide ice could accumulate much more easily than water ice due to the specific temperature and pressure conditions. Or perhaps the entire star system where it formed had a fundamentally different chemical makeup than ours, with more carbon and less oxygen in the original cloud of gas and dust that eventually collapsed to form planets and comets. The enhanced outgassing visible on the sunward side of the nucleus, the side directly facing the sun, tells researchers that solar heating is actively driving the release of these frozen gases in real time, exactly as expected from basic physics. The green glow puzzle. Around September 7, 2025, observers around the world started noticing something very strange happening. Images captured during and immediately after the total lunar eclipse that night showed 3I Atlas had dramatically changed color. The coma, which had consistently appeared reddish-brown in all earlier observations going back to discovery, was now glowing a distinct, vibrant green. This was not what anyone expected or predicted. Up until that specific point, every single spectroscopic study conducted by both professional observatories and amateur networks had consistently shown 3I Atlas, displaying colors typical of dust-rich objects with certain carbon compounds, mostly reds and browns, with no hint of green anywhere. The sudden, dramatic shift to green triggered immediate speculation and heated debate across astronomy communities about what could possibly be causing it. In normal solar system comets, a green coma almost always means the presence of something called dicarbon molecules. These simple molecules are made of just two carbon atoms bonded together, and they fluoresce a characteristic green color when hit by solar ultraviolet radiation. The process is relatively straightforward and well understood. Sunlight carries enough energy to break apart larger molecules containing carbon floating in the coma, creating these dicarbon radicals that then emit that distinctive green glow as they release energy and return to lower energy states. But 3I Atlas throws a massive wrench into that simple textbook explanation. Observations conducted by the Very Large Telescope in Chile and the MDM Observatory in Arizona during July and August 2025 specifically looked for dicarbon, tricarbon, atomic oxygen, and amino radicals in the comet's spectrum. Those chemical species are the usual suspects for creating green coloration in comets based on decades of research. The instruments found absolutely none of them. Zero detection. So if the standard chemistry responsible for making comets glow green is completely absent, what on Earth, or rather what from beyond Earth, is causing 3I Atlas to emit this vibrant green light? Several competing theories have emerged in scientific papers and online forums, though nobody has a definitive answer yet, and the debate continues. One possibility is that the color change directly relates to the comet's rapidly evolving activity level as it races closer to the sun and heats up. Perhaps entirely different deposits of ice on the nucleus, material that was buried or in permanent shadow before, are now being exposed to direct sunlight for the first time in billions of years. This fresh material might be sublimating and releasing completely different chemical species than were present in the coma earlier in the journey when only surface layers were active. Fresh exotic ices might be venting from newly opened cracks or previously dormant vents on the rotating nucleus. Another competing theory suggests the green color might actually be related to dust properties rather than gas emissions at all. Certain specific types of dust particles can scatter incoming sunlight in ways that preferentially reflect green wavelengths back toward observers, similar in principle to how Earth's atmosphere scatters blue light to make our sky appear blue. The dust composition in 3I Atlas might be fundamentally different from typical solar system comet dust. Some researchers have even speculated about exotic photochemical reactions happening specifically in the carbon dioxide-rich environment. Maybe the highly unusual chemistry of 3I Atlas, with 8 times more carbon dioxide than water, is creating molecular species that nobody has ever accounted for in standard comet models. These might be compounds that simply do not exist in typical water-rich comets, but can form readily under these alien chemical conditions dominated by carbon dioxide. Blasted by the sun. Just when scientists thought 3I Atlas could not get any stranger, nature threw them another curveball. On September 19, 2025, the sun erupted with a massive coronal mass ejection, a violent blast of plasma, magnetic fields, and charged particles hurled into space at incredible speeds. These events happen regularly as part of the sun's natural activity cycle, but this particular CME was heading directly toward where 3I Atlas would be in its orbit. NASA's Enlil model, a sophisticated computer simulation that tracks the movement of solar material through the inner solar system, predicted the CME would slam into the comet somewhere around September 24th or 25th. Astronomers worldwide immediately recognized this as an unprecedented opportunity. Never before had scientists been able to watch in real time as a coronal mass ejection collided with an interstellar visitor. When the CME finally arrived, it hit 3I Atlas with the full force of the sun's fury. This was not a gentle interaction. A coronal mass ejection carries billions of tons of superheated plasma traveling at speeds exceeding 1 million kilometers per hour, along with twisted, tangled magnetic fields strong enough to strip material away from a comet's nucleus. Scientists watching from Earth held their breath, genuinely uncertain whether the comet would survive the encounter intact or fragment into multiple pieces under the assault. The magnetic fields threading through the CME could interact violently with any magnetic properties in the comet's nucleus or its surrounding cloud of ionized gas. The plasma itself could heat the coma to extreme temperatures, potentially causing explosive outgassing or even structural failure if the nucleus had weak points or was already cracked from thermal stress. As observations came in during and after the predicted impact time, researchers found something remarkable. The comet survived, but it did not emerge unchanged. Observers noted that the tail, which had been growing steadily for weeks, appeared disrupted and potentially partially eroded by the passage of the CME. The green coma seemed to fluctuate in brightness and extent, suggesting violent interaction between the solar material and the comet's gas cloud. Some researchers reported possible signs of enhanced activity, as if the CME's impact had shaken loose fresh material from the nucleus or opened new vents. The collision provided scientists with invaluable data about how interstellar comets respond to the harsh environment of our inner solar system. 3I Atlas formed around a completely different star, possibly with different levels of stellar activity and radiation. This might have been its first encounter with such a violent solar event, and watching how it responded tells us something important about the structural integrity and composition of objects formed in alien planetary systems. The event also highlighted just how dynamic and unpredictable the inner solar system can be, and how lucky we are to have caught this particular moment in 3I Atlas's journey through our neighborhood. Missing non-gravitational forces. So, yes, comets are messy, and that messiness usually shows up in their orbits in a very specific way. When a comet's nucleus heats up from solar radiation and starts releasing jets of gas and dust, those jets act like tiny, uncontrolled rocket engines. They give the comet small pushes in different directions that alter its trajectory in ways pure gravitational calculations cannot predict. Astronomers call these effects non-gravitational accelerations, and they are such a standard feature of comet behavior that researchers routinely include them when calculating orbital paths. If you ignore these forces, your predictions about where a comet will be in the future quickly become wrong. But 3I Atlas is breaking that rule, and nobody is sure why. Scientists analyzed 4,022 separate observations collected from 227 observatories scattered across the globe, covering the time period from May 15th through September 23rd, 2025. They compared the predicted gravitational orbit with the actual observed positions night after night. The difference between prediction and reality, what astronomers call residuals, came out to essentially zero. In other words, despite actively shedding huge amounts of material and building a coma that rivals Jupiter in size, 3I Atlas is not experiencing the non-gravitational acceleration that should be pushing it around. This absence is deeply puzzling. One explanation is that the jets of gas and dust shooting out from the nucleus are somehow perfectly balanced around all sides, canceling each other out so there is no net push in any direction. But that would require an almost impossible level of symmetry. The nucleus would need to be perfectly spherical with ice distributed evenly across its entire surface, which seems highly unlikely for a natural object that formed billions of years ago. A more probable explanation is that 3I Atlas is significantly more massive than its activity level suggests. If the nucleus is very dense or much larger than current estimates indicate, the momentum imparted by those outgassing jets might simply be too small compared to the object's total mass to produce measurable changes in trajectory. Think of it like trying to push a car by throwing tennis balls at it. The tennis balls carry momentum, but the car is so much heavier that they do not move it. This has led some researchers to propose that 3I Atlas might not be a typical ice and rock comet at all. It could contain a substantial core of much denser material, perhaps rock or even metal, far larger than expected for an object displaying this level of cometary activity. If true, that tells us something important about the incredible diversity of small bodies that form in other planetary systems. 3I Atlas might represent a class of object we simply do not have in our own solar system, or at least have not recognized yet, formed under conditions or through processes nobody has considered before. The Mars Encounter. As September turned to October 2025, the focus of intense scientific attention shifted dramatically from Earth-based telescopes to a completely different set of observers positioned millions of kilometers away. Spacecraft currently orbiting Mars are about to get an incredibly rare opportunity. On October 3rd, 2025, 3I Atlas will pass within 30 million kilometers of Mars. That distance is roughly 80 times farther than our moon orbits Earth, so there is absolutely no danger of collision or even any detectable gravitational interaction. But 30 million kilometers is close enough, barely close enough, for the sensitive instruments aboard Mars, orbiters to attempt detailed observations that have become completely impossible from Earth. The European Space Agency operates 2 sophisticated spacecraft in Mars orbit, perfectly positioned for this historic encounter. Mars Express has been faithfully orbiting since 2003, carrying a high-resolution stereo camera and a spectrometer called Omega, specifically designed to identify chemical species from millions of kilometers away. The ExoMars Trace Gas Orbiter, which arrived in orbit in 2016, brings even more specialized tools, carrying two complete spectrometer suites called Nomad and ACS, both meticulously designed to detect trace gases with incredible sensitivity. Between today and October 7th, both spacecraft will dedicate precious observation time to 3I Atlas, carefully turning their instruments toward the comet whenever their orbital positions allow. What makes these spacecraft observations particularly valuable, possibly irreplaceable, is the viewing geometry they provide. From Earth's perspective, 3I Atlas is rapidly sinking lower into twilight, getting closer to the sun's position in our sky. That angular separation, which astronomers call solar elongation, is shrinking to dangerously low levels. But from Mars, the geometry is completely different. These spacecraft will have clear, unobstructed views without any interference from overwhelming background sunlight. The observations could potentially resolve the nucleus itself as a distinct point of light physically separated from the sprawling coma, finally providing direct size measurements rather than indirect estimates. The instruments could precisely track how fast various gases are being produced over time, revealing whether activity is steadily increasing, unexpectedly decreasing, or showing sudden bursts. They could measure detailed properties of individual dust grains through polarimetry, analyzing how light becomes polarized when bouncing off particles. And they could directly observe how the solar wind, that constant stream of charged particles flowing outward from the sun, physically interacts with and shapes the comet's extended gas atmosphere. Perhaps most exciting, if 3I Atlas exhibits any unexpected dramatic behavior during this window, like sudden brightness outbursts, asymmetric jetting from active vents, or even structural changes, the Mars orbiters might capture it with detail absolutely impossible from Earth. For astronomers trapped on Earth's surface, time has run out. By mid-October, Earth-based observations will effectively cease entirely as the comet passes through Superior Conjunction, moving to the far side of the Sun from our perspective. For several long weeks, it will be completely unobservable, hidden behind our star's overwhelming glare. During that frustrating blackout period, 3I Atlas will reach perihelion on October 30th and begin its journey back toward interstellar space. Whatever happens during those crucial weeks will occur largely unobserved from Earth with no way to gather data, making the Mars observations happening right now even more critically important as potentially the only detailed monitoring during the comet's most active phase. This strange and fascinating journey of 3I Atlas raises more questions about the origins of this mysterious visitor. What do you think about its unpredictable behavior and the theories behind its rapid brightness and strange green glow? Drop a comment below to join the conversation. Don't forget to hit those like and subscribe buttons. Thanks for watching.